how it basically has happened and things like that, and what made it happen is important. And I'm going to go from the past to the present, and then I'm going to walk a little bit to the future. Because some people, you might have heard this thing that people say that Moore's law is dead, right? Have anybody heard this before? Is it Moore's law, this kind of thing that basically has fueled the semiconductors for some long time? Nah, finished, it's dead. Totally untrue. Today, if you basically go in most of the companies that you go around that do design, digital design, they might run a 35 nanometer technology approximately, right? That's kind of the state. Some of them 65. So between 35 and 65 is where most of the companies are. If you're working for a company like Intel, you might do 22 nanometers. That is actually the latest processors which are coming out are 22 nanometer type of designs. Now, I was over actually at Intel last Friday, and some of those designers are already doing transistor design in 10 nanometers. It's not going to happen tomorrow. You're not going to see these products. This is about 3 generations ahead of where we are today. And they're already making transistors that are working. They're already making memory cells that are working, and so on and so forth. So it's very clear, and there's no reason that the end should be at 12 nanometers. Well, there might be some discussion. We'll come back later about the economics. But there's no reason it should stop there. We can make transistors at 8 nanometers. We can go to 5 nanometers below that. Then it becomes iffy. Because you start making a transistor which is almost the size of a molecule. You start getting to some physical boundaries. But by then, we might have some new devices or new interesting things to do. So bottom line is, we're going to keep on scaling for another 20 years. 15, 20 years, guaranteed. It's going to happen. Because as long as people see benefits in it, they will keep on doing it. And there's no real physical reason why it could not happen. So we're going to keep on scaling. And that's really what the history is about everything about digital design is scaling. So these are the questions that we are asking ourselves is, what made digital IC design what it is today? What has changed over the years? What are the things we have been changing? And that's why this class also is changing over time as well, because things that worked really well 10 years ago might not work anymore today, or might be coming back in popularity 5 years from now. It's kind of changed. Sometimes you have cyclical effects. And will it change in the future? That's kind of the things I'm going to talk a little bit about today. So let's talk a little bit about history first. Digital computing. Actually, the first digital computer was built in the 1800s. Well, it was not really built. It was invented in the 1800s. It's a person called Babbage in England who built a purely mechanical computer. Extremely clever. And instead of using transistors or anything like that, it used gears. Now you can see the picture right here. You look at that. This is one of those gears right there. So what you notice right away on this gear is that you see the numbers 0, 1 to 9. This was not a binary computer. All computers today work with zeros and ones. Now, this computer worked with a decimal system. It had 10 positions on any gear, 10 positions that determines the numbers. And then by having dividers between those gears and how you basically combine the gears together, you could do addition, you could do multiplication, and so on and so forth. It didn't need a battery. The way you operate it is you crank it. You had a crank on the side, and you basically put your equations in there, and then you crank it a couple of times, and out comes the result of your computation. Very clever, actually. This thing had already something which is called pipelining. If those of you who have done 150 have heard about the word pipelining. So an adder was not done in one shot, but it was done in 2 stages. And they overlapped the 2 stages, which is typically what pipelining does. So a lot of things. He never built it, really, because it turns out, if you looked at the cost at that point in time, 25,000 mechanical components. That's a very complex mechanical machine. And the cost at that point in time was estimated to be about 20,000 pounds. These are 1,800 pounds. not today's English pounds. Fortunately, he wrote it all down. He made the plans and made them available. And then 150 years later, somebody really built it. So if you go to the British Science Museum in London, you will see one of those things standing there. Yes?
There's also one in San Jose.
There's also one in the Computer Museum? Yeah. It's very clever. It's a very interesting machine. So, but the basic principles were already there. So some of the principles of computing that we're going to be using these days were already available at that point in time. And then nothing much happened for quite a while. There's actually, in the 1900s, there were smaller versions of this. There were calculators you could buy, which were basically the same concept. It was like a little coffee grinder, about this size. You put basically, you moved some thumb wheels around, and you moved some numbers around, and then you cranked the thing a couple of times, and you could do logarithms with it, you could do multiplication with it, a whole bunch of interesting stuff that could be done. So there were some smaller versions later on in the 1900s. Now, as I said, not much happened since then, unless in the early 1900s, there were obviously, before that, a person called Boole had come up with Boolean logic and showed that you could have binary zeros and ones, and you could do manipulations on them. And you have AND and OR function, all these kind of things. The first ones to really use this were something you wouldn't expect. What do you think would be the first application of Boolean logic that was really used in practical circumstances? Any idea? You never can guess it. Huh? No. Close. It was the railroad system. They had a large problem. Right? You have trains going on tracks. You have to figure out that you have one train coming in this direction, train coming in this direction. That's not very good, right? They go head on. So you have lights, red, green, orange, or something like that. How do you control those lights? Well, what they did is basically using, they actually implemented a logic system based on relays. Like a train comes in a certain direction, it basically says, well, it turns on a relay. A relay is a magnetic component that basically up closes. It's basically a switch. And using those switches, I can start building logic. So the first one to actually build logic, but it was electrical logic, not mechanical, but electrical logic was basically using for basically train systems. And they did fairly elaborate things, basically AND or XOR type functionality by putting some of the devices together. But it's kind of primitive, it's big, you have to have a magnetic coil, and basically when the current flows through, the switch closes, the current disappears, the switch opens up again. It was only till 1930s, vacuum tubes got developed. Vacuum tubes, the first type of devices that provide gain, electrical gain, electronic gain. But vacuum tubes were primarily used for radios. That was the big goal of vacuum tubes, is either amplifiers or radios. That's what you use it for. It was only till about 1930s that people start realizing that with a vacuum tube, I also could actually start doing logic. And the first application of this was late 1930s. There were some wars happening. And the most important problem that they had to be solving at that point in time was, if I shoot something, where will it end up? So, and you basically shoot something, you have a parabolic equation, and it adds up on some point. If you know the force, and you know the overall angle, you can basically figure out what it adds up. Solving those equations was the biggest problem at that time. So they built computers for it, with vacuum tubes. And the first computers were really ballistic computers. Computers built out of vacuum tubes that basically can do this type of things. But then from there on, it says, if I can do this for ballistic equations, then I can use it for general purpose problems. And then some other people came along, like John von Neumann. John von Neumann discovered the concept of an instruction set, and so on. So they could load the instruction set machine, and they started building computers. This is the first computer that was actually ever built that was became semi-commercial, the ENIAC, in 1946. And you can see it's a complete room. And the way you program it is with wires. By connecting different things together, you put wires in there, and throwing some switches. Not very reliable. This thing probably has a couple of thousands of vacuum tubes. Every vacuum tube basically produces about 50 to 100 watts of heat. So you can imagine these things were quite warm and had to be cooled. Otherwise, they would break down very rapidly. But the vacuum tubes typically broke down on a very regular basis. But it was the first big computers, IBM took it over. IBM in the 1950s, 1960s, created a whole bunch of computers based on vacuum tube logic. But as I said, the problem was the price was really expensive, and it produced a huge amount of heat. So, going forward, the next breakthrough was 1948. Shockley, Bardeen, a couple of people over at Bell Labs in New Jersey invented the transistor, the bipolar transistor it is. And you can see this is the first transistor ever made. It's an amazing device. It's a couple of layers of PNP material. So no, it wasn't N. No, it was a PNP transistor. You put P material, N material, P material, stack it on top of each other. You need to be able to contact to it. They couldn't find anything better than paper clips. So you can see right there. Here is your connector, right here. Paper clip molded on there, soldered on there, and bingo, you have a vertical transistor. And it worked. So this is a Nobel Prize. This got somebody a Nobel Prize, and it was worth it. Obviously, it was something that changed the world substantially. Again, the first transistors were used not for digital logic, but for analog functionality. It created the first transistor radio. It was a big breakthrough. It was from radios which were building with these vacuum tubes in there. Suddenly I could have a small radio. You could get AM and FM reception. Huge breakthrough. Companies like Texas Instruments were born because of that. So, clear that out. Now that's nice, but it's not very scalable. Right? One transistor is good. You can make an amplifier with it by putting a couple of those transistors together. You're done. But if you start doing digital, you have to go one step further. This is not a scalable business model yet. Not something that's going to create a huge industry. So the next breakthrough, which also got a Nobel Prize, was the idea that I can actually put, if I use the right processing methodology, manufacturing methodology, I can put a couple of transistors in the same plane of silicon. I take a piece of silicon, a wafer, and I start doing some processing steps. I actually can put multiple transistors in that same plane. It's called the integrated circuit. While this is a discrete circuit. So two people invented it at the same time. You have Noyce at Intel and Kilby at Texas Instruments. Both of them came up with the same similar idea approximately at the same time. So they are called co-inventors. Unfortunately, Noyce died before the Nobel Prize was given, so it's only, you cannot get a Nobel Prize when you're dead. So only Kilby basically got the Nobel Prize for the invention of the integrated circuit. But the key idea is indeed that now you can take a piece of silicon and you do subsequential steps on it. I'm going to talk a little bit about manufacturing later on, because it's going to be important if you start understanding how physical layout works. But this is an example of one of the first circuits. This is by Motorola. It's a 1966 circuit that does actually, it's a 3-input gate implemented using bipolar transistors. So you can see the transistors, every one of those little squares here, these are all bipolar devices. So we have 6 transistors in one circuit, and the rest is basically contact holes and basically wiring. So that was the first thing. 1960s, bipolar digital logic. And what you got is a family. You could buy, at that point in time, you could go to the store and you could buy a 2-input NAND gate, 2-input NOR gate, XOR gates, some flip-flops and things like that, discrete components. And then you put them on a board and you can build more complex things. Now bipolar was nice. It was easy to manufacture. PNP, NPN transistors. You could actually, they're nice transistors. You get good gain out of it. But it had a couple of problems. Number one, if you remember, I think you've seen bipolar transistors, right? They still talk about bipolar transistors in 105 a little bit. Bipolar transistors have a disadvantage that if you make them operate, there's always going to be, anytime you want to do something with it, there's current flowing through them. And you have to bias it. You have a base, and current has to flow into that base if you want to have collector current. So what it basically meant is that a circuit built using bipolar transistors typically is always going to consume a lot of power. Even if you don't do anything, there's current flowing. The second thing, so that creates heat. And heat is, as we all know, is kind of the enemy of reliable design. So there was also problems with reliability. So bipolar transistors were good, but to a certain point. Comes 1970. 1970, or 1969 actually, one of the leading companies in 1960s in integrated circuit was a company called Fairchild. Fairchild had a number of people, really bright people, who kind of had jumped ship first they were at Bell Labs. They left Bell Labs, started a company called Fairchild. And then in 1968, they jumped ship again and started a new company. This is Bob Moore, Noyce, Bob Noyce, and the third one I'm trying to find his name right now. It escapes me, but there's three people who started a company called Intel. And Intel basically, the claim to fame of Intel is we're not going to use bipolar, we're going to use MOS transistors. And using MOS transistors, actually we can put a complete processor on a single die. That was something unheard of, because before that IBM was building all those very fast computers, mainframe computers, by putting a lot of bipolar chips together. So it's large boards with many components together. Intel said, no, if you use the right manufacturing strategy, and if you look at the crystal ball, we should be able to put more and more of those transistors together on a chip. This is going to change the world dramatically. So in 1971, the first microprocessor was born. It was a very simple microprocessor. I think I have a picture here. Here it is. This is the 4004 from Intel. 2,300 transistors. Compared to what you could do in the 60s, is a huge number. For today, this is kind of ridiculous. It's something you kind of generate in 30 seconds. 12 millimeters square, completely designed by hand. This is really piece of art. Somebody was drawing all those lines by hand. Not really spectacular in speed. 740 kilohertz. And not a most advanced technology. You could actually look at the chip and you could see the transistors. Right? 10 micron is something that you almost visually can't figure out. You could see the lines and the transistors. But it was really a breakthrough device. It's a 4-bit microprocessor. So every data word, everything, if you want to do something more precision, you have to do sequential steps. But it was a fun thing to play around with. It was hard to program. I programmed one of those guys, the 4040. It was a real pain to work with 4-bit microprocessor, but at least it was a microprocessor. So that's one thing. The same year, another thing happened. Intel, again, same company, also launched the first semiconductor memory, an SRAM memory. That basically, so now you suddenly had memory, and you had microprocessors. You could start thinking about doing complex things. And the rest is basically history. I'm just going to flip to some pictures here. This is 2005. It's one of the Pentium 4 processors. That's 125 million transistors, 3.8 gigahertz, 90 nanometers. Now, you can imagine, number one, not a single one of those lines is drawn by hand. That's one thing. It's all done by computer. It's very patterned, and you basically cannot see anymore what's going on. This thing is getting so complex. It's kind of amazing. This is 2006. Suddenly, Intel, it's kind of interesting to observe what happened over time. We went from bipolar to MOS for a very good reason. The reason that our MOS was adopted, even though it's not such a good transistor as a bipolar one, is the fact that you actually can have logic happening. If you don't do anything, you don't consume any current. You don't have this base current that you need for the bipolar device. If I put a voltage on a transistor, I can get a current flow and it gets to equilibrium. Things should not consume any power anymore. So the main reason we went from bipolar to MOS was power. And that basically helped for quite a while. Then we went from NMOS to CMOS. We're going to talk about it in the mid-80s. And again, people say, hey, no current anymore. It's going to be good for power. And in the 1990s, we started running again into power problems. That's why in 2005, Intel suddenly went away from a single microprocessor chip to a dual core. It's purely because of power reasons. Might be unclear at this point in time, I will show it later, of why things like dual core, quad cores, and things like that were a necessity. It's something that they couldn't get around. So dual core was very simple. They put two processors, exactly the same design. If you look at it, you have, let me get one of this other, I need this, So you have one processor here, and the other processor here, and they're exactly the same. By the way, this is cache memory, so half of your chip is memory in this case. And that's true for most of the microprocessor. Memories are the dominant component in the overall design. This is one of the latest, 2011. This is the Xeon processor, 64-bit. Oops, close that. 2.6 billion transistors on the die. Not a small die. 500 square millimeters, so that's about this big. It's a big chunk of silicon. It's really amazing that they can make this thing work with this complexity. And there's a whole bunch of tricks to make it work. It's not just trivial. 32 nanometer technology. What you notice, however, is that the clock frequency is 2.4 gigahertz. It's not faster than the previous generations. Actually, what we'll notice, and we'll discuss that, clock frequency has flattened out over the years for, again, power reasons. But this is kind of the state of the art. The newest things that are going to come out, as I said, are going to be 22 nanometers. Fundamentally different than this in terms of transistor structure. You might have heard about this. Suddenly, Intel has gone three-dimensional with the next generation, basically using a transistor, which is not your traditional flat transistor anymore, but something that's a vertical device called a FinFET. But we'll talk briefly about that later. This is 22 nanometers. This was a chip that was shown in 2009. This is a memory, showing that actually you can do memory design in 22 nanometers. This is 2.9 billion transistors. And you can see the memory cell here. This is the SRAM cell that's basically being used to design this thing. So that's where we are today. Around 20 nanometers is really the state of the art. And it has really shown that by basically carefully road mapping things out, planning things out, building methodologies, we actually have gone from simple concept and basically be able to build on it, 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 such a way that we can still now design chips, even with teams which are not 1 million people, but basically a couple of hundred people. Kind of summarizing this is kind of a famous picture in the sense is that if you put all those designs that I showed you on a map here, and here you have our 4004, 1970, early 1970s, 1,000 transistors, a couple thousand transistors approximately. Then we have the 8080, the 8086. Then comes the Pentium class devices. Then you really got to go to Itaniums, dual cores, and so on and so forth. Now, if you plot the number of transistors on a log scale over time, you see that you get a straight line. Right? This is what's called Moore's law. What it says is that the number of transistors we can put on a die is doubling with a certain rate. And the rate that Gordon Moore predicted was about every 18 months. Basically, in 1964, he made a prediction that says that given manufacturing methodology, understanding of how these things are processed, it should be able for us to basically double the number of transistors every 18 months. And it's pretty amazing, right? It has happened. Now you can say this is self-fulfilling because we say we have to double every month. People will work really hard to make it happen every 18 months. So that's really what the road mapping does. It makes a target for people and they're going to make sure they make that target. But it's still quite amazing. This is about 1964 when he basically predicted it, and now we're 2012. We're talking about 60 years of a sustained law. So even more amazing, this is Moore's law, even more amazing is that this is the log. Basically says the number of transistors on a chip is going to double every 18 to 24 months, which basically is saying that the semiconductor technology will become double its effectiveness every 18 months. Because if you think about it, you can double the number of transistors, and if you can do that for the same price, that means that the cost of your transistor will keep on dropping, 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 dropping. It means that for the same cost, I'm going to get more functionality, or basically I'm going to get, for the same functionality, I'm going to get it cheaper and cheaper every time around. That's kind of the key economic kind of conclusion from this. And we're still used to that, right? We expect a new device to come up every year or so. I want to get a new iPhone every year that's faster, that's more features. It's a mindset. It's something that's now so ingrained in our thinking. Everything that's information technology should improve every 18 months, approximately every 2 years. We should have a fundamental change in this thing. An amazing factor is that Gordon did this on an extreme extrapolation. You're scientists, you've gone through some science, right? You know how you basically can do statistics, analysis, and things like that. At the time that Gordon Moore was making his prediction, he had 4 points that he has measured. In 1959, basically 1 transistor, and then 3 transistors in 1962, and about 4 in 1964, and so on and so forth, and 5. So he had 4 points. He said, okay, now this looks like a line to me. So let's extrapolate it. Bingo. So this is the basis, and this is based on the 1959 to 1964 type of timeline. And it still holds. Now, actually, if you read his original paper, he basically never made that prediction that it would go that far. He says, you know, I can predict that this will continue given what I know about the manufacturing process, which is based on lithography and silicon wafer processing. I can predict it's going to go till about 1975. After that, nobody knows. But it turns out that indeed it was even more visionary than he predicted. Now, as a result of this, the things have been amazing, right? So think about it. This happened not only for computation, but also for memory. If you basically take your little iPhone device on this or your iPad and you get used now to 64 gigabyte of flash memory. That's huge. If you think about that memory, what you can store in there is amazing. Right? Basically today we can store virtually anything you know, everything you need to know can be almost stored on a single device. And again, it's a result of the fact that we've been making our memory cells smaller and smaller and smaller and put more stuff together. So this is again the same thing. If you look at memory, we've seen the same trend. It's basically a logarithmic trend. We double the amount of memory on a die every so many years. Now, same thing had been happening with frequency as well. So it was an unintended side effect. You make a transistor smaller, obviously it becomes cheaper if you can do more, right? So cost is kind of cool. Frequency was a side effect. But if you make something smaller, other things happen. Some other good things happen to you. The transistor gets faster. And the reason it gets faster is for a couple of reasons. You get a shorter channel, so your carriers don't have to go that far. You get less parasitic capacitances. Capacitance is going to be determining a lot of our speed, so they get smaller too. So your whole thing, basically your device, you can switch the device faster. And that's true. FTs of MOS transistors, the unity gain type of frequency, has been increasing over and over and over and over again. Today we're talking about devices that basically have FTs of 250 gigahertz or 300 gigahertz today. So as a result of that, you can switch things faster. A gate, a basic function like an inversion, becomes faster and faster and faster. Today we're sitting at approximately how much? What do you guess? What's a single inverter, 35 nanometers? How fast do you think approximately would switching speed be? Any guess? Microseconds? Nanoseconds? Picoseconds? What's your best guess? nanosecond. Think about it, gigahertz microprocessor. You have to be faster than that, right? It actually is a couple of picoseconds. And it might go below picoseconds in some of the next generations out there. So we're really sitting at switching speeds of the single gate in this picoseconds rate. It's really fast. Now, if you think picoseconds, then you say, wow, gee, if I have a inversion that can switch in a picosecond, then a multiplier can maybe take 40 picoseconds. So we should be able to do microprocessors easily that are at 20 gigahertz. It hasn't happened. Actually, around the year 2002 approximately, we're at 4 to 5 gigahertz, and we're still at 4 to 5 gigahertz today. Hasn't changed anymore. Why was that? Very simple. And you can see it on this curve here. It actually plots it very nicely. If I put a linear curve to here, goes up and up and up. And with the dual core processor, suddenly it flattened out. And the only reason for that is if you would have gone faster, your chip would melt. Very simple. The power dissipation goes to the roof. You don't want to have a laptop with a processor that consumes 500 watt. Laptops are already hot enough when you put them in your lab. They would basically burn you. And your chip would basically die very rapidly. That was the biggest problem. And around the year 2000, it really started running into what's called the power wall. And power, or heat dissipation, is limiting the performance of a device of today. It's the biggest challenge. And this is one of the things that has changed over the years. So this was a prediction actually around the year 2000. It says, gee, if that's when they started realizing that power was an issue. It says, boy, we have used a lot of tricks to manage power dissipation in circuits. And as a result of that, power has been gone up like Moore's law. But then they realized suddenly other things started to happen that this would even accelerate. So by 2008, we should have an 18 kilowatt microprocessor. You need a little nuclear plant next in your laptop basically to make it run. Never happened obviously because nobody would buy a thing like that. So they got smarter and they figured out again on how to basically either go back to linear or even better, go down. Because one of the things that happened at the same time is we used to have desktops, and in desktops, big box, fans, blowing all the time, you could cool it. Then you went to laptops, a little bit trickier. You still can cool it, right? Your laptop has a fan somewhere that occasionally kicks in, so you can cool it with air. Then you went to those devices. Have you ever seen a cell phone with a fan in there? Would not be very practical, right? So you have to have devices now, you have to have compute power without any cooling or traditional cooling strategies. So we were forced to think about how can we get the power down again for these mobile processors, things that go into iPads and things like that. Again, all basically require a path like this. So we're going to talk a lot about power in the semester, and basically what are the techniques that we can use to get performance without blowing that power up to 18 kilowatt. Clear it out. Go to the next one here. So same thing here, not much, same picture actually. So no extra information. Now here's another one. It's the same equation basically. Power density, actually power is not the most important thing. It's power density. Suppose I have a chip, you have a small chip versus a large chip, basically how you can cool it depends upon the surface area, as you can imagine, right? You have a chip that gets hot, it radiates the heat. If I have to radiate it over a larger area, that's a lot easier to cool it out than something that's very small and basically puts it all in one area. So what really matters is power density, the power you consume per unit area. And if you look at some of the strategies, actually, again, if we wouldn't have basically gotten smarter and think about power, already around 1995, a number of the chips run basically about the temperature of a hot plate. Hot plate basically you put a pan on it, you put some eggs in it, and you can boil them. But if you would have done anything, you would have seen these things going that by 2010, the temperature on top of the chip would have been the sun's surface type thing. So again, that didn't happen. Your chip would melt way before that. So we have managed to kind of keep it flat again. Even though you look at some microprocessors, you will see that, say I take your Xeon processor, the one that I showed you, about this big, and you will, while it runs, you put an infrared camera on it. I basically look at, infrared basically tells you heat variations, right? You will see that some parts of that chip are relatively cool, where there's memory. Memory tends to be cool. Where you have the processing device, where you really do the computation, that's going to be quite hot. There you can have power densities that are typically sitting around here. You can actually sustain, with some cooling, temperatures, power density about 300 watt per square centimeter. But not over the complete chip, because then you use the rest of the chip to dissipate the heat out. But again, we're going to talk more about heat later on. So that's what happens when you don't do the right thing. This is from a very famous, I might show you that video later on. What happens when you take the cooling fin of a microprocessor. This was an AMD chip. Take the cooling fin off and you start running a game on it or something like that. After about 5 seconds, you see a little smoke kind of cringing up, and then suddenly it starts melting, and the whole board melts, and you're done. I've seen another beautiful demo of people who have a board with FPGAs. It was vertically mounted, and suddenly all the chips start falling off. They have basically desoldered themselves. And obviously the system didn't work anymore. Now today this won't happen anymore. Again, if you basically are audacious, what you can do is take one of your smart devices, open it up, and if there's an Intel, like your laptop or your desktop, and take the cooling fin of one of those Intel processors and see what happens. You won't see smoke. I can guarantee you that. What you will see is that the Intel device is going to be clever enough to say, hey, I'm getting really warm, I'm going to just go slower, and ultimately says, I'm quitting. I'm not doing anything anymore for you, it's too hot. So it has automatic temperature control. But we'll talk a lot about those other things as well. But basically power, performance, area, cost, these are the type of things we're going to play around with. So I explained I've been scaling over 40 years, Moore's Law, 50 years. Every 2 years or every 18 months we reduce the dimensions by a factor of, or the complexity of a circuit increased by a factor of 2. Now, how do you get that? Well, actually, if you look at the minimum feature sizes, so you might ask yourself, why do we go from 130 nanometers to 90 nanometers to 65 nanometers to, 40 nanometers to 28 approximately, then to 22? Why those weird numbers? Where do they come from? Who picks those numbers? And actually it's quite simple. Every generation of technology tries to scale down the minimum feature size with a factor of 0.7. Sounds like a weird number, 0.7, why do you pick that? But if you think about it, 0.7 squared is 0.49, is 0.5. Means every time I make the feature size 0.7 times smaller, my area goes down with a factor of 2. So the same function scales with a factor of 2. And that's really what you're trying to do. Every time, double the amount of functionality per unit area from generation to generation. And that's why those technologists, every time they start thinking about a new technology generation, they say, okay, factor 0.7. Now, in theory, that also means that your cost is going to decrease with a factor of 2 as well. If I make my area 2 times smaller, you would think that the part is going to be 2 times cheaper. And that's true in general, but not completely, as we'll discuss later today. There's more things that basically contribute to cost than just the area of a chip. But the area of a chip is important. So it's been a beautiful model, right? So for the same function, so many years, what we've done is for the same cost, you double the amount of functionality every 18 months. That's why you expect every time you have a new iPhone to come out or whatever it is, or a new microprocessor, you expect it to be 2 times better than the previous one. For the same money. You don't want to spend more money. The money is fixed, you get more functionality. Or the other obviously would basically be to keep the functionality fixed and hope it gets cheaper and cheaper all the time. Which happens, right? Certain functions that used to be expensive 20 years ago are now taken for granted. right? Because they're so small you don't even see them anymore. Things that basically used to be complete chip are now somewhere in the corner. If you think about it, that first microprocessor I showed you last lecture, the 4004, today if you make it 4004 and make it an advanced process, it will be smaller than one of the bonding pads. It will have vanished completely. So I could put probably 10,000 or 100,000 of those processors on a die without a problem. Right? So the cost of those things has become zero. So that's the other factor, basically. The same function gets cheaper and cheaper and cheaper and it's taken for granted. So as a result of that, in a device like this, you can put more and more functionality in there because some of those functions are basically almost obsolete. So that's the interesting thing. Now, there's a challenge with this type of things. And as I said, you would expect from a cost perspective that you automatically get area goes factor down with a factor of 2, so cost should go down with a factor of 2 as well. But that's not really the case, because if I make a chip larger and larger and larger, or more and more transistors, and assume that a single designer designs a fixed number of transistors per day, right? So that's productivity. And say I can design 20 transistors per day or 1,000 transistors per day. So every time I make my chip 2 times more complex, you would expect that you need 2 times more designers, if the designers don't get better, right? And as a result of that, if you think about it, we used to have a team of maybe 50 designers for a microprocessor 20 years ago, but now that microprocessor is about a factor 1,000 times more complex, you would expect to have teams of about a couple of 10,000 people per processor. And if you keep on going like that, you would expect that all the designers in the world might work on a single chip. Right? Because it gets so complex, you add more and more people to it, the teams become just unwieldy. So that's not possible. So in order to basically deal with this issue, we have to make sure that our designers get better all the time. Right? You have to get more efficient. So the way you do that is obviously by changing the way you do design. In that 4004, again that I showed, there was a piece of art. Every single line was drawn by hand, and every transistor got touched many times by many people. Today, that's impossible. Most transistors that are on those complex chips have never been touched by a human whatsoever. You basically generate them. There's computer tools that help you. So designers, instead of basically sitting there and playing around with single transistors, they are going up in the higher levels. They basically use better tools, higher level abstractions. Nowadays, a simple microprocessor, like an ARM processor, is a building block. You take it from your library and say, oh, I need another ARM processor. Bingo, throw it out there. It's not as simple as that, but it's getting close to this. So you're starting to work with larger blocks and putting your design together by larger functional blocks. So as a result of that, you become more efficient. So that's really important. Productivity is an important factor in design. Now, I just want to show you that we're going to talk a lot about microprocessors, but if you think about where the real business is today, microprocessors are still a good business, but if you look at what's happened in certain areas now, like for instance, media tablets, it used to be all in PCs and things like that. Media tablets, smartphones, you look at the numbers that have happened over the last couple of years, it's staggering. While PCs have been kind of flat, actually last year they dropped by 5%. Smartphones basically are skyrocketing. And a smartphone today has probably a quad microprocessor in there, or at least a dual core microprocessor. Tablets, this thing is not even, I think if you look at the line here, the light blue line, shows that tablets should be 200,000 by 2015. Totally obsolete. Actually, it's already larger than that right now. So those things are basically going up. So the markets that are driving basically the development of those new complex components are changing year after year as well, and basically are going to other domains than traditional computing. So that's really what I wanted to point out. If you want to do design today, you want to do a complex chip, there's two things you have to address. On one side, as I mentioned, your transistors are not anymore the transistors of old. You're starting to get devices that are getting so small that they're basically going to some microscopic limits. You start getting to levels that noise, crosstalk, reliability, manufacturability, power dissipation, clock distribution. Just imagine a chip of 2 centimeters and you have a clock signal traveling from one part of the chip to another side of the chip. And you try to clock this at a couple of gigahertz. The delay of the wave traveling from one side of the chip to the other side becomes important, because the speed of light over 2 centimeters is already becoming a factor, right? So you're starting to go to all those type of things that have to do with the very small. And I think that's going to be part of this class, is looking at how can we deal it from a design perspective in such a way that we still can make reliable designs in the presence of all those microscopic effects. But on the other side, I have the pressure that I have to start building complex designs with the same size of team in shorter amount of times. Today, the pressure on the market is really big. You want to get a new part out every year, definitely in the consumer world. In the PC world, in the past, you could work a PC and use it for 3 years. Today, you change smartphones every year approximately. So the pressure in those companies to get new complex parts out quickly is becoming an issue. So this whole issue about how to make a complex design in a short period of time and get it to market as fast as possible is the other side of the equation. So it's a very interesting type of balancing factors that has to happen here. Yes?
What was the DSM? What does that stand for?
Deep submicron. So it's a terminology that people came up with about 10 years ago. Nowadays, I would call it nano. It always depends on terminology, right? Submicron was kind of 100 nanometer type of design. But then nowadays, we're at 20 nanometers. So it's really deep submicron we're going. And so people call it nanotechnology. From the time actually nanotechnology officially is everything which is smaller than 100 nanometers. It's called nanotechnology. What's in the word, right? Anyhow, good question. Sorry for that. So this productivity trend I basically talked about. So this is a key thing that I'm going to basically start to instill throughout actually the next couple of lectures already. If you think about design, I can definitely think about transistors, right? Transistors level, and oops, let me go to the previous one here and let me get my pointer. There we go. So, did I turn it off? There we go. So devices. That's the way you typically think. I build a transistor, put a couple of them together. Then, with a couple of transistors, I can build a circuit. I could gates, NAND gate, NOR gates, whatever, memory cells, and so on and so forth. All right, so you first bring a couple of transistors together, you get some circuit, the circuit becomes a gate. From that time on, you kind of ignore the fact that there's a switching device. You just start playing around with Boolean equations. That's the next level. So you start building designs. It's going to be a collection of NAND and NOR gates. I forget about the transistors below that. Next level of abstraction is, well, gates are fine, but I don't really care about gates. I care about multipliers, adders, memories, data paths. These are the type of things. Video encoders, you name it. These are modules. And then the next level up is you start thinking about systems. System is, what is the total functionality do I try to accomplish? It's going to be a couple of microprocessors, some large memory subsystems. There might be some accelerator blocks on there. There might be some wireless interfaces on it. That's the system level. So as a designer, you have to be able to think through those layers. Most designers that do digital design today are going to be somewhere here. If this guy comes with me, somewhere here. You think about modules, sometimes but most of the times you don't think about gates because you're going to use tools to generate all the stuff below it. Though you have to be very careful, because if I now say I'm write a piece of code, C code, Verilog code, VHDL code that does a certain function. I synthesize it, out of it comes a block. And suddenly I start doing analysis, I just start doing simulation, and I see this thing is not fast enough. Or this thing uses too much power. What do you do? Well, if you only have that high level of perspective, you don't know, you don't realize what is the cause of this power dissipation, what could I do to reduce power. I don't realize where the critical bottlenecks are so that I can make it faster. So having that capability of looking through those layers all the way down to a transistor is very important. If you don't do that, you end up with designs which are going to be mediocre. So understanding the basics, what determines speed, what determines power, what determines reliability, is going to be very important if you want to build complex systems.